보통 이런 이벤트 하게 되면 10분 정도는 다들 늦으셔서 첫 번째 그 말씀은 10분 후에 시작하겠습니다 이러는데 오늘은 딱 7시에 시작을 할 수 있을 것 같습니다. 오늘 지금 날씨도 굿인데 400여 분이 신청을 해주셨고 그리고 대기자가 저희 온오프믹스 보면은 한 250분 있었던 것 같아요. 오늘 정말 뜨거운 열기 느낄 수 있고 저희가 그에 걸맞는 훌륭한 분을 모셨습니다. 저는 구글 프로덕트 매니저 이혜민이고요. 예전에 이제 마이크 슈스터하고 함께 한국어 음성 검색을 론치를 했었던 인연이 있어서 오늘 소개를 맡게 됐습니다. 오늘 톡에서는 국내에서 공개적으로 저희가 소개를 하지 않았었던 그 구글의 머신러닝 오픈소스인 텐서플로우에 대해서 그 개발 과정과 그다음에 향후 구글의 머신러닝의 방향성 이쪽에 대해서 말씀을 하실 거고요. 오늘 스피커는 마이크 슈스터 박사시고 마이크 슈스터 박사는 현재 구글의 리서치 사이언티스트로 일을 하고 계시고요. 독일에서 전기공학을 전공하고 일본 나라 첨단과학기술대학교에서 음성인식학 박사를 하셨습니다. 그리고 2006년 구글의 음성 검색 팀으로 조인을 하셨고요. 현재는 구글의 브레인 팀의 멤버로서 텐서플로우와 그다음에 구글의 머신러닝에 대해서 계속해서 일을 해오고 계십니다. 오늘 참고로 오늘 저희가 공지를 했듯이 오늘 강연은 영어로만 이루어질 거고 통역은 없습니다. 근데 제가 조금 좀 천천히 혹은 중요한 부분은 이렇게 리핏을 해가면서 해달라고 부탁을 드렸기 때문에 여러분께서 큰 문제 없이 들으실, 그다음에 발표 자료도 있기 때문에 들으실 수 있을 거라고 기대를 합니다. 그러면은 welcome, Mike Schuster.
Okay, Haemin, thank you very much. I'm really glad to be back in Korea. So the last time I was here was about 5 or 6 years ago when we launched together the Korean speech recognition. And that was a lot of work and a lot of fun at the time. So, and then about 2.5 years ago, after working on speech recognition for a long time, I joined the Google Brain team, which at the time was just starting. And that's what I'm going to talk about today, about our products, about how you can use it, and so on. So I don't know how many of you are experts and how many of you are total beginners. And I hope I can say something for everybody. So I first have a simple example of machine learning just to understand what the meaning of machine learning really is. Because a lot of people, I think, especially who haven't studied computer science or something like that, for them it's often hard to understand what do you mean by machine learning. So I hope that example can clear it up. So then I will talk a little bit about neural networks at Google. What we do with them and how they were developed. And then we talk a little bit about problems and data. So Google has a lot of data and what kind of data and so on. So then we'll talk a bunch about TensorFlow, which is our large-scale machine learning toolkit. I have some examples of models, what you can do with them, what types of models exist. Then we'll talk a little bit about TensorFlow open source. This is our open source offering that we launched in November 2015, so just about 6 months ago. And I have some final remarks. So first, a very simple machine learning example. So think about like a problem. Let's say you have, you want to predict the temperature from the brightness outside. So you have a sensor hanging out of your window, and you don't want to open the window. You want to know what is the temperature outside. So in that case, usually what people used to do was they look at a few examples and they try it out and they say, okay, they make a rule-based system that you find rules that solve the problem. So for example, you build a little box that says if the brightness is between 3 and 4, then the temperature is 15 degrees, and so on. You make a lot of those rules, you put them on a chip, and there's your product, right? So this is actually an okay approach for simple problems, maybe like this one, but it's impossible for harder problems because it doesn't scale. When you have high dimensionality, when you have a lot of data that you cannot look at that cannot be looked at with just a human, this process doesn't scale at all, and that's why it doesn't work for bigger problems. So for the machine learning approach, you collect lots of data, here brightness x and temperature t, and you can look at it then maybe in a chart just like here. All the blue dots is your data, and then you pick a model to predict the temperature from the brightness. And this could be just a straight line. You could do anything else also, but let's say we use just a straight line, and everybody did this in school, linear regression. So what is the best line? And the best line you find by minimizing the prediction error is basically the distance from the blue dots to the line. And once you minimize that function, and minimizing functions is something you also learn in school with calculus, then you can solve this problem, and this is just simple. The simplest problem at all is just linear regression. And this approach with more complicated functions and more data and more difficult error functions scales well to harder problems. And that is basically what machine learning is about. So about neural networks. I worked with neural networks already like 25 years ago. And 30 years ago, well, I didn't work with them 30 years ago, but it's very interesting to see the progression of what happened. So 30 years ago, we had models with hundreds or thousands of parameters. They were trained on hundreds and thousands of examples. We used simple pre-built model architectures like, just feed-forward neural networks. They were, for those of you who are computer science people, a single thread, single machine. The training time was days to weeks. The reputation at the time was only crazy people work on this. And also there were very few people working on it. I remember that, I went to a lot of conferences and I always met the same people. So the same, maybe 10, 50 people. It was really interesting. So today we train models with billions of parameters, trained on billions of examples. We have very complex model architectures, which are usually dynamically configurable, multi-layer networks, recurrent RNNs, LSTMs, convolutional networks. We'll talk about some of those later. It's multi-threaded, it's multi-machine training. The training time hasn't changed. It's still days to weeks. And this is human patience. How long can you wait for an experiment to finish? It cannot be more than a few weeks, right? The reputation today is that neural networks can solve any problem. Not true, but we'll talk about that. And today there are really thousands of people working in this field because it has proven to be very useful. So why did it improve so much, right? And I think the two most biggest reasons are that it's more learning from data, so it's the machine learning approach and not rules that has been applied more and more. And also a very big reason is just faster machines. So 20 years ago, I used a huge machine that was as large as this room to train a basic recurrent neural net. And today we can do this on our phones, basically, right? So machines have become very fast. Everybody now has a GPU card, and just more people are working on it too. So deep learning at Google. Our mission was to build infrastructure to train and use large-scale neural networks with large amounts of data. because usability and the speed of the tools is very important. As I said already, you need a fast turnaround time, no research or development without it, right? So most experiments have to run in hours or days to really make progress. And really only very high profile stuff, very high profile experiments can afford to run for more than a week, because really nobody has the patience and people just forget what happened like a week ago or 2 weeks ago. So the history of the group was, it was formed in around 2011 with just a few people, maybe 5 or so. The first system was running within a few months. The distributed system running on many machines was running soon after that. There's actually a paper about this. You can look it up if you want to. Today it's not that interesting anymore, but at the time it was a good description of our system. So today we have lots of people. We have, I think, more than 130 now. We have an infrastructure group. We have research people. We have a support group. We have education. We have, you know, a group that takes care of the online stuff, of the open source community, and so on. So it's a lot of effort. Also, what is interesting is that a significant part of Google's global compute power is used by neural net related projects by TensorFlow. So in all the data centers that we have in the world, a few percent, I don't know how much it is right now, but it's pretty significant for a company like Google. So you may have seen this picture before, because Jeff gave a similar talk a while ago. But so we have, this really shows how much growth there is within Google for the use of deep learning, and TensorFlow in our case. So the number of directories, the time is on the x-axis. The number of unique directories is on the y-axis, and you see it looks really exponential. So it's now 1,200 and more directories just at Google with TensorFlow or disbelief code. So it's used in Android, in apps, in Gmail, in image understanding, in maps, for NLP projects, for photos, for speech, for translation, for YouTube. I mean, it's unbelievable how many applications there are. And many of those, of course, it doesn't have to be Google, right? It could be anywhere in your startups and whatnot. Okay, so let's take a look a little bit at the data and the problems that especially Google is looking at. But for many of you, this may be similar. So first of all, we have lots of raw data available. In text, we have trillions of words of English and other languages. Visual data, we have billions of images and videos. I think for YouTube right now, there's more than 60,000 videos are uploaded every day. So, you know, can you imagine how much data that is? In audio, we have tens of thousands of hours of speech per day that comes in and is, you know, actually, I don't think actually all of it can be stored because it's just so much data. There is a lot of user activity. So people type in queries, they mark messages for spam, they do all kinds of things, they click on ads, you know, they do all kinds of things on the internet. This is stuff that could potentially be useful. Also what we have is what is called the knowledge graph, which is basically just billions of labeled entities. So for example, the word Obama and the word president are linked because Obama is a president. And so you have all these entities and they are somehow linked with some kind of relationship. So this is what we call the knowledge graph. And we need a system to just make better sense of all this to help our users. So, and this is only possible when building really large models with large amounts of data and relatively quickly. So in terms of data, images. So this is a lot of like typical images that we would see. And you see this system, there's a stone wall on the first one, so it actually shows where the stone wall is with a probability of 0.95 that this is a stone wall, right? For the second one, we have a dishwasher, a car show, judo, 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 in 3 cases, tractor, tractor, tractor. And you can see that the probability of seeing a tractor, for example, varies from 0.91, 0.91, and then this one is more of a tractor than the other two of 0.94. But this is just an example of what kind of data people see, right? So this is, these are typical images that the classification system would see. So here's another interesting example that we have. For example, when you have Google Maps and you want to show exactly on the map where people live, right? So where certain addresses are, you need to know what number is exactly at what point. And this has been historically difficult because often maps are wrong and you know, it's not exactly right. So what Google did was we have Street View and we take a picture of everything. And then we look through the videos, find the numbers, the house numbers in the videos, and that is what these pictures are. Then we find the number itself, the digits itself, make a little box around each digit. And then after we have done that, we classify each digit to find the house number. And because the original Google Street View has a GPS system, we know exactly where it was on the map. And then we can put this number on the map, and we know, for example, number 64 is exactly right here. And this is very useful. But you can imagine that this is a difficult problem. I mean, for humans, it's relatively easy to read these numbers. For a computer, it's a lot harder. So here's another example that just shows what kind of data we're looking at. So if you are in New York and you have a picture of this, you can now, if you have a good system, you can now find, for example, for men's suits up here, or for gifts down here, or a souvenir store, or there's a lot of things that you can understand from this picture. You can understand that there's a tree here. And if you want to put all this stuff on the map, it might be useful to people. So another type of data is not images, but text data. So text understanding is, of course, for Google, hugely necessary. So just some typical questions that we could ask is, what language is it? Is it a question or not? Does it contain the answer to question X? What is the answer? Can the text be simplified? What's the translation to a different language? What comes likely after this text? Is this text positive or negative? Can this text be generated from just a few keywords? And so on and so on and so on. So all these are questions that product teams at Google ask to make somehow a better decision for the user. And it's not only 10 things, right? It's probably 1,000 things that different groups are working on that just look like this. Okay, so let's talk a while about TensorFlow. And this is a little bit more technical. Maybe some of you know all this already if you have read, the TensorFlow papers, but for some of you it might still be relatively new. So TensorFlow, our first system was called Disbelief. And our second system is called TensorFlow. It was built for very large amounts of data, very large models, very flexible model architectures. So all the data we just saw for image, for speech, for text, for classification, for regression, all these different types of data we wanted to handle with a single system. It was made for quick prototyping of ideas, but also once you have a quick prototype, to be able to run it in production with possibly hundreds or thousands of servers, such that it can actually serve a whole country or even more than a whole country. So it runs on the desktop, it runs on servers, it also runs on mobile, it runs multi-core, multi-GPU cards, and I'll talk about those details a little bit later. And since a while ago, since about a month ago, it also runs multi-machine distributed, so meaning You can, set up your 16 machines or however you have, and however many you have, and train one model with all those machines at once. So the open source version was released in November 2015, and some of you may have looked at the website. What was interesting was that a big result about this system was that it is a lot faster than our previous system. So many of the big models that we have are 2 and more times faster than with our previous tool. Okay, so we'll talk a little about the TensorFlow architecture. So the core is in C++, and the reason is because it's very low overhead. Probably all the main people in the team use C++ for almost everything. I think it's the right choice for the low level operations. So then we added different front ends for specifying and driving the computation, and we'll talk about that in a second too. And those are today Python and C++, mainly Python actually, because the C++ front end has not been used so much yet, and it's pretty easy. Well, it's possible to add more. So this is how that would look like. You can drive your experiments and all your computation through Python or through C++. A little bit more about the TensorFlow architecture. So traditionally, machine learning systems were often limited and built for a specific case, right? So you had few possible model structures. And I'm sure that if there are researchers in this room, they have built and wrote code for a very specific structure. For example, for recurrent neural nets, or for convolutional nets that can only do classification of images, and so on, right? This is okay, of course, but if you have in a company like Google, where we have all these different data types, it's actually very useful to combine all these things and make a single system that everybody can use. And that was our goal. So also the data types, right? We wanted to handle images. We wanted to handle possibly 3-, 4-dimensional data. We wanted to handle sequences, video sequences, anything you can imagine. So we can also do that. Then optimization criteria is the same thing. You want to have a very flexible system where you can easily change your optimization criteria and have it still work without hacking all the code. So with TensorFlow, we can do all this. And the computation is defined as a directed acyclic graph, a DAG. Some of you may have heard of this. And this is to optimize an objective function. And I have an example later that shows this. So what is important, and this is what took many of us a while to understand, is the computation model. So the graph is defined in a higher level language like Python. And then the graph that describes the computation is compiled and optimized. Some nodes are merged and some edges are removed and so on. And then the graph is executed in parts or fully on all the available low-level devices. And that could be CPU or GPU or many machines, or it could be phones or something like that. Okay, so this is probably the next simplest example, and many of you have probably seen this. So this is not linear regression, but logistic regression, very similar. It's often the basic model for classification. So you have n examples of data, you have inputs, and you have target of a given dimensionality. You pick a model with parameters, and in our case, we call them weights and biases. And in this case, the model looks pretty simple. It's y equals softmax, which some of you may know. It's actually not so important what that is, of the weights times x plus a bias. So it's basically linear plus the softmax. And typically, people use cross-entropy loss to minimize this. So this is just a specific definition. because it fits well the softmax and it fits well the classification problem that this usually represents. And then what we have to do is we have our function, our loss, or error from the slides many before, and we need to minimize it by gradient descent. And this requires to calculate the gradients of the loss with respect to the parameters w and b. And this is the problem that we have. So in TensorFlow, we could almost type this in as is, and TensorFlow would do most of the rest, right? So TensorFlow does automatic differentiation of these expressions. And the gradient calculation is done by TensorFlow once the model and the loss is defined. So in a graph, how would that look like? So we have a graph of nodes, and we call them internally operations, right? Just ops. And these blue things here, the matmul is a matrix multiplication. You have an add, you have a softmax, and this all goes then with the target to the cross entropy. So this is the first part. Those are the nodes. And then we have also the edges. So the edges, the arrows here, are n-dimensional arrays, which are commonly called tensors, right? So one-dimensional is a vector, two-dimensional is a matrix, three-dimensional is a tensor, four-dimensional is a tensor, five-dimensional is a tensor. So, and this is what is very handy to have in arbitrary dimensions. Okay, so this is only for the forward graph. So what do we do for the backward graph? So for the forward graph, we put in the inputs and calculate some outputs. Then we compare that with the targets, and now we need to calculate the gradients, and we go back through the same graph. By going back through the same graph, we add additional nodes to our original graph such that we can do the whole thing in one go. And this is how a part of this would look like. So the backward graph and the update of the parameters later are added automatically. And you can think of it just as additional nodes and edges in the graph. So why is this a good way to look at things? So one reason is that it's once you have a simple graph that you can store on disk and you can look at, it's easy to decide what parts can run on what devices. So for example, you can run your device A for all the green nodes, and you can run your device B for all the blue nodes. And you can do this in parallel if you choose them wisely. And in this case, it could mean distribution across threads in one machine, across processes on multiple machines, or within one machine, across several GPU cards on one machine, and across, of course, many machines if you have them. That is our way of thinking about this, because it simplifies the interface of thinking about this stuff a lot. So here is the data flow graph for real problems. Looks a lot more complicated. And this is just a simple example here, but you can already see that the graph itself looks kind of complicated, right? All the edges are basically matrices with data flowing. And the nodes are all kinds of stuff, a matrix multiplication, a activation function, a bias is added, and so on. So in practice, these often have hundreds or thousands of nodes and edges. And inference means in this graph to just execute the forward path of the graph. So some people ask, so what does inference exactly mean? It's just the forward path, right? That's what that is. So it would just, in this case, it would calculate it up to here, right? So let's write this one here. Okay. Now a little bit on the simpler side, so the devices. Well, this runs on phones. It runs on single machines with multiple CPUs and possibly multiple GPU cards. It runs on distributed systems with many hundreds of GPUs. So here we have a picture of a data center. Sometimes we have like 100,000 machines in one data center. Nobody could use a whole data center for one problem, but you can use, many to actually solve a problem. And some of our problems use a lot of compute power. So the use of GPUs. Google has really thousands of GPU cards installed in data centers. And it was for a long time, it was a big discussion whether we should do this at all. But finally, people understood that GPU cards are very good to use because they're cheap, relatively cheap, given the computation they give us. So many models are today trained on GPUs because of the speed advantage. The typical speed up over CPUs is up to 10 times faster on average. So if you train an image model that usually takes 2 months to train, you can now do it in a week. And that is very useful. So typical use per model training is that we use between 1 and 32, we call them replicas. Those are machines. And then we use 1 to 8 GPU cards each. In some cases, we have models that are trained on hundreds of GPU cards total for a single model training, and it still takes a week. But those models have, almost 1 billion parameters, so that's why it takes so long. So some examples of models, and this goes back to the data that we saw before. So it's using basically some of the same data. So one typical example is, and a lot of people understand this easily, is just object recognition. So you have a picture of something, let's say a cat, and what you want is the name of the object. And that's exactly what this thing does. You put the picture in, and what you get out is actually the probability of that this is a cat. So here we have a chart over time. This is from a benchmark. It was called ImageNet. And in 2013, we had about 57.5% top 1 performance on this pretty difficult task. This is like about 1,000 classes on the output side. And just a year later, basically, it was at 72.5%. So there you see how, and this was just because of better architecture, better training methods, maybe longer training, all kinds of improvements. But here you see how fast it has improved. The predicted humans are still much better at this, but actually by now it's 2016, I'm actually not sure where this is today, but I think it's now the error is below 10% and probably very close to human performance. So how complex are these models? Image models especially are very complex. So here's in the middle, we have just all the little boxes of nodes that you see. So this is 24 layers deep in this example. Now it's actually more. And each of those boxes still contain, 6 separate convolutional layers. So there are many, many, many parameters. Some of them are shared because of the convolutions. But it's a very, very complex graph that you see. So this is the architecture that won in 2014 the ImageNet, and it had 6.6% top 5 error rate, which means in 94% of the cases or 93% of the cases, the top 5 contained the correct answer, which is very good given how many classes there are. So for example, many of you, if I wouldn't show you what this is, would probably not know which flower this is. But the machine knows. So the machine says left is hibiscus, right is dahlia. Okay, we all know it's a flower. But this is pretty good for a machine. Because think about the background, and it's really not so easy to decide this unless you have a garden and know these things. So also generalization is pretty interesting. So these pictures look very, very different, but the machine understands this is a meal on the left and on the right. See how different these pictures look like. And somehow it figured out this is a meal. So here is also an example what kind of errors the system makes. And this is something that probably kids would do too. If you ask a kid what the left thing is, it could say snake, but it's not a snake, right? So on the right, the system found this is a dog. Well, it looks like a dog a little bit. If you are like a 1-year-old kid or 2-year-old kid, you would say maybe that's a dog. But it's not a dog, right? It's a cow. So how do we use, for example, this specific ImageNet, right? So in practice, in Google Photos, you can type in keywords, and it will find the keywords in your photos. It will look for those keywords. So for example, on the left here, we have statue. So it would do, in this case, it's of course just an example, but all the statues of that the person took a photo of will show up. And sometimes it makes mistakes, of course, right? So on the right here, we have sea. You want to see all the sea pictures that you took in Santa Cruz and Jeju and whatnot. Here you have them. So here are some more examples. If you want to look for all your drawings, right, you can type in drawings and it will find all the pictures that you took a long time ago of your kids' drawings or just your own drawings maybe. Here on the right, people were looking for Yoda. So Yoda, and you know what they found, actually this is Yoda, but maybe not the one they were looking for, but still, I mean, the system could actually find the doll that looks like Yoda, right? It's great. So we talked about pictures now. Another very interesting part of models is just sequential models, sequence models. So models for sequential data is for what is sequential data? Basically anything that has a time dimension. So like speech, or, well, it doesn't have to be a time dimension. It could be text, you know, of varying length. It could be user actions. It could be stock quotes. Could be a lot of things. So for those, there are two very important models, which are all called recurrent neural nets, RNNs. And then we have recently those have been used a lot. More complicated recurrent neural nets. They're called long short-term memory neural networks. So those are possibly also bidirectional and have multiple layers. But here's just a very simple architecture that on the left, we see the unfolded architecture. So they are recurrent because they go into one activation, and then the activation is fed back to itself and fed back to itself again, and then the output comes out. So if you unfold this over time, what you see on the right, you see, you know, this would be the one for t minus 1 and for t plus 1. And all recurrent neural nets basically look the same with a more complicated structure here. So what can you do with these models? Even the simplest models you can use for these things. So in practice, they are more complicated, but you know, the concept is the same. So in this case, we feed in a pre-processed waveform of like arbitrary length, and it goes through the network, and you get out a sequence of English letters, or in fact any letters, right? In this case, you know, you say this is a cat, and it would spit out this is a cat. So you can train these networks to do exactly that. Of course, in any language, right? This is just the data is different, but you use the exact same network. So now, if you use that same network, this exact same structure, you can also use for translation. And that is what makes this so interesting. So you put in an English sentence, the quick brown fox jumped over something, and you get, you know, a sentence in French, which sometimes may contain errors, but it's still, you can use the exact same model structure, and that's what makes this interesting. We are actually right now running a translation project which hopefully works exactly like this, and it hopefully will improve all the translations by a lot. So then we have, in 2014, we ran some benchmark results for translation. And this simple idea actually worked pretty well. So state of the art at the time was 37 points, blur points they're called for the translation system. And our neural translation model got 37.3, which is, doesn't look like much, but it's a significantly improved translation, and people would probably notice. There are some papers about this if you want to read about it. Of course, there are tons of papers about translation systems, but this is just an example that talks exactly about this benchmark. So now we have talked about the image models and the sequence models. So what, if you put them together, what can you do? So in this case, this is really an interesting example that even made it, I think, to the New York Times. You put in an image, and it produces a description of the image. So in this case, this picture there, and what came out is a close-up of a child holding a stuffed animal. And this almost sounds like magic. How can the neural network learn things like that, right? But the trick is you just have to feed it enough data and provide it with the right data, and then it can probably learn things like this. So there's also a paper about this. And on the next slide, I have some examples from a benchmark that we ran. And so I have to say, this is a relatively restricted benchmark. So it worked for some examples very well. For others, it didn't work so well. So look at the first one. A man holding a tennis racket on a tennis court. If you look at this picture, this is hard to understand that this is a tennis court. I mean, kids, well, may know this, but to produce this description is pretty good. The second one here, 2 pizzas sitting on top of a stovetop oven. So apparently it can count. It knows it's a stovetop oven. It knows it's on top. So it's pretty amazing that things like that it got right. Or here, a group of young people playing a game of frisbee. I mean, they are young, but they could be old people too, but it's probably better to put in young, and that's what the system found here. But also, I mean, if you look at the last example, a man flying through the air while riding a snowboard. Okay. Not really, it's a kite, right? But it could be a man on a, right? Could be. But I mean, it's just amazing how within Google we had a demo that people could put in random pictures and just see what it gets. And after a while, we found that the system was actually pretty limited because there was a relatively small database, and it would produce the same stuff over and over again that often had very little to do with the pictures. But it at least showed that it's somehow possible to go in this direction. And I'm sure if we would have bigger networks and if we could train them, if we could have much more data, we could train probably a pretty good system. And I find this pretty amazing. And this was all basically the same models, right, that we already had. Okay, so I gave a talk yesterday at a different place, and they asked me to talk a little bit about AlphaGo because I know it was such a big deal in Korea. So many of you know this. It's a super complex and I think beautiful game. I don't play much myself. My brother plays it a lot, and he apparently watched all the games 6 hours each at home. It's unbelievable. I mean, so why is it so complex, right? Chess has roughly 10 to the power of 50 positions. Go has roughly 10 to the power of 170 positions. So the number of atoms in the universe is 10 to the power of 80. there you see how difficult, how many positions there are. It's just, you cannot imagine how many positions there are. And that's why people thought nobody could ever solve this, right? But it's actually, I didn't find it surprising at all. I mean, it's a combination of position evaluation, meaning you look at the board and you say, how likely can I win with this position? That's number one. You give it a score, right? And then the next thing is tree search. You try out all possible next moves. And you do this, if you do the combination of position evaluation and tree search, you can design pretty easily a strategy that wins on any of those games, like chess or Go or checkers or whatever it is. So the better the position evaluation is, the less tree search is needed. And humans happen to be very good at position evaluation. They can look at a board and can decide, hey, this is a very good position, and if I do this next move, it's going to be even better. And computers are very good at tree search because they're so fast. So they can try out, thousands, millions of positions in a second maybe. Maybe not in a second, but if you have many computers, then you can do it in a second. And so the trick, it's not really a trick, but what AlphaGo did, what the people did who programmed it, was they learned a very good position evaluation for a computer, not for a human. A human is much better at the position evaluation itself. But they just learned a very good position evaluation from many previously played human games. They had a huge database of Go games. And then they had the system play against itself and other programs to improve on the position evaluation. And that is what made it so good. So there's really no magic. I mean, I've had so many people who say to me, wow, this is amazing that it can beat it. But I think it was obvious that computers would win at some point. Maybe not this year, maybe not next year, but it just happened to happen now today. So today I talked to Hemin or to somebody else and said, people today are not surprised that a computer can add up 1,000 numbers immediately, right? No human can add up 1,000 numbers immediately. You think it's completely normal. Of course, every calculator, every little program can do it. But 50 years ago or 100 years ago, people will go like, no, that's impossible. And this is similar with this problem. So it's, I don't think it's bad. I mean, maybe it's a little bit sad because, but there will be other challenges that are very, very difficult. Okay, so TensorFlow open source. This is again a little bit more technical. So the capabilities, many of you have tried it, you already know, but the people who haven't tried, it usually runs on Linux. It also runs on Mac OS X, also in virtual machines. I've tried that. So in Windows, you can install a VMware and run it, and install Linux in VMware, and then run it on that Linux. It runs on mobile, on Android, on iOS. Now I've heard on Raspberry Pi, although I haven't tried it. For the GPU cards, it supports a lot of GPU cards, K20, K40, K80, Titan X. This is usually only supported under Linux currently. It uses, well, at the time, CUDA Toolkit 7.0 and CUDNN greater equal version 2. I think by now they're up to version 4. It runs multi-core, multi-GPU, and multi-machine. The TensorFlow Python API is usually Python 2.7, but if you compile from source, you get 3.3 or more. It has the typical neural network modules that you need. And if you know something about neural networks, none of this is a surprise to you. There's the sigmoid, ReLU, 2D, 3D convolutions, and there's a whole list of things with documentation that you can see. It has a lot of losses that are predefined, cross entropy, L2, L1, so which is basically mean squared error and things like that. You have various optimization algorithms that we found useful. Of course, gradient descent with or without momentum, AdaGrad, there's Adam, there's a whole bunch of optimization algorithms also. And For resources, there's of course the website. If you haven't looked at it, take a look. And many people ask questions on the mailing list. Usually many of those questions are actually answered in the documentation that you can find on the website. So it's very good to first look at that. There are tutorials, there are examples, there are some pre-trained models. We try to add more so people can run whatever their projects are from some pre-trained models. For example, the image models take a long time to train, and if you have something that already works, you can do easily other projects with that. So there's a TensorFlow white paper that describes the basic idea. The code is at GitHub, which is, of course, typical for any open source today. There's support at Stack Overflow, which is a user community where everybody helps each other, and that seems to work quite well. There's a discussion mailing list that we support. A lot of people in the Brain team are actually on that list and see it. And some people also ask questions there, but I would it's probably better to ask on Stack Overflow because there's just more people see it, and it's the chance that it actually gets answered is greater. So one thing that is maybe not surprising now anymore, but people asked us, so Google is a public company. Why would they open source software? Isn't that's crazy? But so there are many reasons for that. But one thing is, and some of them are listed here. So machine learning is becoming more important really every day. So in every company you look at, whether it's a cement mix company or a Samsung or any company you can think of, there are many machine learning opportunities. And giving out a free general tool makes it easier for many to participate, and it pushes the boundaries and is really helping research and industry at the same time. So allowing everyone to express and share their machine learning ideas using TensorFlow code leads really to more rapid research and better sharing of ideas. Also, what is interesting, and this may be surprising to you, but the open sourcing helped ourselves to organize our own software and documentation better. So a lot of people think that at Google everything is very clean and organized and planned. That's usually not the case. Okay, it's usually very messy. Documentation doesn't exist. Things are redone several times and stuff like that. So with the open sourcing, we went like, we have to make an effort to make this really good with documentation and everything. And actually the whole team sat down for like a week and wrote documentation, or many of the team. And this was really good, because now even inside of Google, we point people to the outside version because it's very clean. Then another reason is the community helps to improve TensorFlow. And there are already many amazing examples of TensorFlow in the research community, and especially actually from Korea. I've seen on the mailing list, there are some guys that have done amazing things, which I found surprising after really like days or weeks only after the software came out. So I have some final remarks. People often ask us, so what is Google's approach to machine learning? Why does it work so well? I mean, I don't know whether it works that well. It somehow works, and there are lots of problems that you don't see. But one thing that is, I think, a little bit special is we try to be a very open company, outside and inside. There are really very few secrets. I mean, most of the things are not secret. It's just complicated. And the systems are often so complex that nobody understands everything. In our group, we have 130 people or so, and I can guarantee you nobody understands everything. So the people, there are three things I think that are important. So Google tries to hire good people from everywhere, and last time I looked, 70% of Google Brain was not born in the US, which I find pretty amazing. I mean, there are not that many foreigners in the US, maybe less than 10%. And given that there are 70% are not from the US, it's really kind of amazing. So another thing is that I found is that it often takes only very few people to start a project. Like 2 or 3 people together can start a new translation thing or start a new whatever it is, right? Another thing is that we do is we try to work on scale. So scale is very important. If you only work on problems that have 100 examples, you probably get stuck very soon. But if you have a problem that has millions or billions of examples, then you can actually improve for a long time. So that is important. And also is diligence is one thing. So many projects that we start with really bad performance, like speech recognition, I remember, started with like greater than 80% errors. It didn't work at all. But we just said, hey, it can only get better. And you iterate and improve and track progress over time, and every week or every month you look at this, oh, it got better by 10%. And this is in the end how it becomes really good. So what's next? Of course, machine learning will be used more and more because it really simplifies many problems and only relies on learning from data. Applications, I think, will be understanding pictures and videos in real time. Currently, probably impossible for many. We will have better translation, better speech recognition, better speech synthesis. We will have help with decision making, like driving. Health is a huge topic. Everyday tasks that you do on your phone and otherwise. And finally, I just want to say that because it has been machine learning has been such a big thing in the media recently. Be skeptical of anything that people claim that works, because it's usually very, very hard to make things work. Ideas are really easy. Oh, you should do it this way, you could do it that way. True. But to make it work we find is often very hard. It takes a long time. Thank you very much. And questions?
끝나고 별도로 시간은 없으실 것 같아서 30분 동안 필요하신 질문 있으면 꼭 지금 해주시면 됩니다. We will have 30 minutes to ask the questions.
Also, you can ask the question in Korean and maybe she can translate it or somebody else.
Could you explain the difference between TensorFlow and other neural network library, for example, Caffe? So in other words, why I have to use TensorFlow instead of Caffe?
Right. I would say try them all. Okay. So it's not that hard usually to download Caffe or download Torch or download something else and just try a simple example. And then in the end, you see which one works best for your specific problem. So one thing that is, I think, so TensorFlow is not perfect for every application. But one thing that is good about TensorFlow is that, first of all, is our second system. 130 people work on this, and there's a lot of support. We try to fix all the bugs. We try to make it faster. There is basically, if I would be a small company and you need to decide which one am I going to use, TensorFlow is probably a good choice because you know it's not going to go away in 6 months, right? There are problems in some toolkits that maybe the authors don't fix anymore because, I mean, Caffe was basically written by one person and later, expanded by more. Torch has also some problems. It's good for many things, but is it really the right choice for your personal large data problem, right? And for that, I think TensorFlow is fairly good. Currently not available in Windows, but so I think there was a plan. I'm not exactly sure what happened to the plan, so I can check, but it's I would recommend if you have a Windows machine, because I have a Windows machine too, you install VMware. It's free, right? And put Linux into VMware, also free. And then you can use at least basic TensorFlow very easily. You can run most of the examples, and that is useful. Yes.
그 이름을 왜 텐서플로우라고 붙였는지.
Excuse me?
Why did you name this package as TensorFlow?
Or why is it called TensorFlow? Because you remember that picture with the arrows? So those are tensors, and they flow. It was just a name. We just had to find some name, right?
You could give the name as matrix flow, and
We could have chosen a different name, yes, but I think it's an okay name.
thank you.
All the examples you gave us looks like only the supervised learning. So I'm just wondering if the TensorFlow can also be applied to the unsupervised learning, or how to optimize with the tensor graph.
You can use TensorFlow for density estimation, which is basically, unsupervised learning. It depends on what you exactly mean by that. When I think about supervised learning, I think about inputs and targets, right? When I think about unsupervised learning, I think about only data. So I want to model the distribution of some data. And that is, of course, that is possible. I mean, your objective function is then log likelihood of some distribution. For example, Gaussian mixtures. You could train with this, right? I have not seen it, but I mean, it's definitely possible. I have seen actually models that train conditional Gaussian mixtures. So if you just take the condition out, it's definitely possible. It really depends on exactly what that problem is, but because this is more a framework, I'm sure it can be done whatever kind of unsupervised learning you are thinking.
Do you know any successful examples of unsupervised learning with TensorFlow?
There is a guy in Japan, otoro.net, and he has done a lot of interesting examples, and some of them are actually unsupervised
One more
learning.
question.
Yes.
In the graph model, looks like if there is a bottleneck noise, then the performance will be very, very low, maybe. So it's affected by the structure or topology of the graph.
Yes, that can happen, of course. So if I think, so the question is, if there is a graph that has a bottleneck somewhere, it could be that the bottleneck makes everything very slow. That's of course right. But in this case, so TensorFlow allows you to put operations everywhere. And you could, for example, for this specific thing, you could shard, meaning divide your matrix multiplication in many smaller parts and distribute it over different machines and execute this in parallel or execute this in different threads. It's not trivial to set this up, but it's possible with TensorFlow. And then, this bottleneck will go away. So it's internally, we know that we can run huge networks with 1 billion parameters very fast. Yeah, go ahead.
Thanks very much for today's your speech. I heard the news, the AlphaGo with the reinforcement training algorithm. So I want to know the TensorFlow. Do you have the plan TensorFlow support the API that reinforcement training algorithm? Like AlphaGo.
Okay, so let me rephrase the question, okay? So AlphaGo, so first of all, TensorFlow was developed in Mountain View. so at the Google headquarters. AlphaGo was developed at DeepMind in London. So that's, I think, 10 time zones away. It's actually very hard for us to talk to them just because of the time difference. Although it's the same company, and we work together, it's still, we don't know many of the people. But they use our software. So they use, they use the disbelief system, they use the TensorFlow system to program, to try their ideas. And actually for AlphaGo, I'm not exactly sure, but it was a mix of their own software plus disbelief and maybe a little bit TensorFlow to get this, to make this work. So there was a lot of development going on their side that we knew nothing about, but they used our tools. So it's definitely possible. It just takes a while to get it done. Yes.
So,
Sorry. Where? Oh yeah, it's okay. It's okay. You have the microphone. Yes. Go ahead.
so I've been wondering about the application or the actual usage of the ImageNet, because I can think of it as a tool to automate the process to tag an image,
Yes, of course.
right?
That's
But Google already I can already search image at Google. I mean, I can search it, right? I can input the keyword, and then the already images are tagged. So my question is, what are you trying to do after this?
Okay, so the question is, the images at Google are already tagged, and what do you do? What else do you do with things like ImageNet? So it's not about this is not the only application ImageNet can be used for, right? There are so many new images every day that also need to be tagged, and maybe the system is better than what we had before. In fact, I know it is. So also, think about videos. Videos have, thousands of frames. You need to somehow classify these videos or understand something about it. And that is, you can run it over all the videos, which of course takes insane amounts of time, but it will be possible at some point. So there is so much data that we haven't applied to this yet, right? And also ImageNet is already running for many of these applications, like when you want to find Yoda in your pictures. So.
Thank you.
Okay, so.
Okay, thank you for your nice introduction to TensorFlow. I've been looking into the source code of TensorFlow, and I'm thinking that your team seems to be borrowing some concepts from some tensor network theories of cognitions. And my first question is about, is it really borrowing the concept of tensor network theories of cognition to implement the neural network algorithms in TensorFlow? And my second question is about TensorFlow as it is. It seems to be in the midst of some deep learning framework and some general graph computing framework, I think. So do you have any plan to develop some more advanced learning algorithms, including reinforcement learning and other Bayesian learning tools integrated with some general graphical models in TensorFlow? Okay, my question is two.
Okay, so right, to the first question, we didn't have a specific architecture in mind when we started this. We just learned over time what could be possibly a good architecture. You may be familiar with the tool Theano that came out of Canada in Montreal. So that tool is, we had some of the developers on our team for a while, and I think some of the design principles were borrowed from Theano, but of course we added our own things. And the goal was to make something usable that is easy for people to use and solve our problems. There may be things that we cannot do easily with TensorFlow, and maybe actually I have some things in my head that I think, well, that could be improved. So we'll see how that goes. Your second question was about the
Yes, it's about your plan to
Right.
make it
Okay.
available, some kind of advanced
Right.
learning algorithm.
Right. Yes. Yes. So think about the group and Google not as a top-down organization where somebody makes plans and then everything is executed. It's more like a group of people that all smart people, and they all have ideas and they all want to do something. And it's not only our team, it's actually in the product teams as well outside that people have ideas and they start new things based on TensorFlow. In fact, on GitHub, I think there are like thousands of copies of TensorFlow already where people try their own things. And this is usually how development works at Google. And there are people who have done simplified interfaces. There are people who have, inside of Google, tried Bayesian models and things like that. But there is nothing planned by individual people. And I don't even know all of the plans. So it's people like you, go out and make some front end, some better, Bayesian front end, and write some documentation and give some examples, and that is how things are made better.
So then you mean that there are some rooms for us to do something?
Of
about those
course,
things.
yes,
Okay,
of
I
course,
see.
it's open source. And
Yeah, absolutely, yes.
of
One more question.
Okay.
Yes. I saw an article about your company's purchase of quantum computer for machine intelligence lab. I think there seems to be some relationship between your TensorFlow work and their work, I think. So do you think that your TensorFlow platform can be ported to D-Wave's quantum computers? Do you think so?
So I don't know much about the quantum computer things that Google is doing because it's really far away from us.
Yes.
But I don't think it's really practically applicable yet, right? And it sounds like it's going to take a very long time before anything really works with quantum computers. So my guess is that for TensorFlow, it will take, I don't know. I mean, there's no plan, and it's really, there are many, many more problems before anything will happen in that direction.
Thank you.
Yeah.
Hello. I have checked the playground.tensorflow.org, and do you know that?
Yes.
And it's actually not made of TensorFlow. It's made of pure JavaScript running on the web browsers. And I thought that such visualization is very interesting for beginners in deep learning stuff. And I want to know if there are any kind of monitoring or profiling components integrated in TensorFlow.
That is actually a great question. So monitoring and especially profiling, for some of you who don't know what that means, is if you have a TensorFlow graph and it's slow for some reason, how do you find out how to make it faster? So internally we have some profiling tools that are quite good, but we haven't made them open source yet. And I think there are some plans to make some of them open source, but we don't have a deadline for that, and I don't know exactly what the plans are. But I know that it's a significant problem that people don't understand how to make things faster, and this is a thing that needs to be addressed, and we are trying to do this. So for your first question, you looked at the playground. If you haven't looked at this, it's an example where you can play with the parameters of a neural net and see how everything improves. And this is really, it shows you a lot about how a neural net works and what you can actually do with it. So I would encourage everybody to look at this one.
Thank you.
Anywhere. It's very hard for me to decide. Yes.
Hello. Thank you for your good lecture. And I have a question. I'm a Mac user, and I tried to combine and run the TensorFlow and the sequence-to-sequence models, but I found that it does not support AMD GPUs because it's dependent on the CUDNN and it's dependent on the CUDA library. So is there any plan to support AMD GPUs?
I don't know whether there's any plan, but I think the problem is exactly as you say, there are so many dependencies on the tools from NVIDIA that, you know, CUDNN and so on, that it's very hard to change all that at once. I mean, we would like to support more cards, but currently we don't. So I don't know. I think this was talked about a couple of times. I think the best solution right now is to buy just an NVIDIA card, you know. In the back there are some people too. Okay. And here's somebody. Go ahead.
What's the requirement to get into Google, particularly in deep learning project? Do I need really good experience or good degree?
It's good to have a good degree, but it's actually interesting how different the TensorFlow team is, okay? So many people are from different countries, and not everybody has gone to a top-level university, right? I mean, people come from all kinds of different backgrounds. If you know, there's not only Google, right? There are many companies that do similar things. There's you know, Facebook, there are many startups. There's really many interesting projects in the world where you could potentially work. But what is important is programming is super, super important. And you know, you would want to solve problems, right? Those two things, I think, and you know, having an open mind is very important, right? So some of the examples that we had, so this year we have a program called Brain Residency, and so it was put out last year in November or so, and a lot of people applied. And 30 of those people, they actually come to us for a year. They get a contract for a year and work with us to learn machine learning and do whatever they like. And hopefully we will do this in the next years too, right? And I would encourage you guys to apply for this if you are interested in machine learning. If you have some background, let's say, you know, even biology or something like that, and you're interested in computers and you know already something that you want to do, then this is a perfect thing to do. It may be hard to get in, but you know, we hired a lot of people which you probably wouldn't necessarily think they would actually get in. But that's what I would say to you.
Thank you.
My question is about your major area, speech recognition.
Yes.
And do you think it's possible for machine to beat human with the further optimization in the area of deep learning, or do you think we need more than that?
So do you want to know whether it's possible for humans to beat, for machines to beat humans in speech recognition? It's actually interesting that I think they're already beating humans, and I give you the reason. Okay, so when we transcribed, there's a lot of data coming in every day, right? And all these people speak different accents, and it's actually the same sentence by somebody spoken in California, somebody spoken in Texas, and somebody spoken in English in India sounds very, very different. And probably many of those you couldn't understand just because you cannot understand the accent. But the machine understands all these accents. So what we found actually, that we had some transcribers in India that our speech recognition was better than the transcribers. So we didn't need the transcribers anymore, right? The people who just listen to the text and write it down. And that had a lot of reasons. One was accent, one was context knowledge, lots of names and things that only people know from a certain area. And there are probably words, actually, when you talk to your brother, there are certain words that nobody else understands, really. Maybe not even your parents. That's at least how it is in English. And so there's a lot of that going on, and we found that the machines are already better. So I know that for if you have a speech recognition app on your phone, it's often still not good enough. It needs to be better, and hopefully it will be. But I'm sure it will take another maybe 5 to 10 years, and there will be very little distinction between humans and machines, I think. Go ahead. For speech? I mean, there's on every Android phone has speech recognition, and I mean, millions of people use it every day. You can, if you don't know how to write, let's say in Japanese, a certain word, you just say it, and you blop, yes, there comes your search result, and it searches Google automatically. You can say, navigate to home, right? And the phone knows where your home is. It finds the best route, it puts it on the phone, and actually gives you the speech synthesis how to go home while you have the phone in your car, right? I mean, it's really very, very convenient to use this. So that's one thing. Okay.
First, thanks for your presentation, and I have a quick 2 questions. And is there any company actually try to use TensorFlow to develop any service and application from that, since it released about 6 months, and I'm not sure, but you heard about those kind of things. Any requests from company and any service field? Because I want to know TensorFlow is suitable for which field. And second question is, there is a Microsoft chatbot called Tay. Is there any a similar service are you planning to develop? Because seems like there are, of course, the natural language process has a high level at Google has, and is that actually can be developed by TensorFlow?
Okay, so the first question. What was your first question? Wait, it's.
First question was just, is there any
companies?
Company.
Right, companies.
Yeah.
So I'm not in the part that talks to the companies, because I develop the software and run experiments and things. But I've heard that a lot of companies actually talk to our cloud team and to many other people. I don't know which companies those are, but big companies are trying, they want to use our image recognition. They want to use our speech recognition. They want to use lots of things that, just work easily in our data centers, and they just want to use an API. So there have definitely been people, I've seen on the mailing list that people in China run 256 GPU cards on one machine and things like that. I don't know what they're doing with it, but it sounds like a more industrial application.
But that seems like only limited in the API system. So that means they have to use on the Android system. So if company want to use different way, there's no company.
So I know that many companies have asked. They download TensorFlow. They use it within their, I'm not exactly sure what they're doing with it. Some financial companies, I mean, it's just unbelievable. The spectrum of companies there are many use cases. I just don't know, and probably even if I would know, I couldn't tell you, because some of this is secret, right? And some of it is just relationships with companies. And the second question was?
Any plans for the chatbot system?
Oh, chatbot, yes. So you may have heard about the Microsoft chatbot. It was actually not very successful, right? It was shut down after a day because it did some stupid things, or people found a way to have it do stupid things. So a chatbot is actually something that is very, very easy to build with TensorFlow, okay? It's basically just a language model. So if you have, you have text coming in, and you predict, you have, an answer and a question and an answer and a question and an answer. So turn 1, turn 2, turn 1, turn 2. And you can just feed in this whole string as a language model. You train a language model, which you can do with TensorFlow today. So you can you can feed in the first part and then let it produce the second part. And then again, you hold it and feed in the next part and so on. It's once you understand the concept, it's actually very easy to do. Whether it will produce something useful is another question, because many, especially more complicated projects, are really complicated conversations, require a lot of knowledge. And all the chatbots are pretty dumb. I mean, they just, they say hi, and they say, what's your name, and stuff like that. But, once you ask anything complicated, there's nothing they can do. So you can try it yourself, but you will see quickly that it's hard to develop something that actually makes sense.
Thank you.
Thanks for your presentation. My research area is speech recognition based on deep neural networks. And recently I tried to train the LSTM model for the feature enhancement in the speech recognition. I have two simple questions. And first is this possible to train the LSTM for the feature enhancement by using arbitrary lengths of speech? Because the examples are use the same length of the data in the language model or the machine translation. My second question is there any helpful material to implement the feature enhancement by using the LSTM?
Okay, so the first question is something, actually, where are you? I didn't see you. Can you hold up your hand? Okay. Oh, you're back there. Okay, I'm sorry. I couldn't see you. So the first question is, and this comes up a lot on the mailing list as well and on Stack Overflow, how do you train a model where you have different length for the sequences? The problem is that you have to put the different sequences in a batch to make use of the greater training speed. And it's actually not so hard to do. So we do this in two different ways. You can either, for example, for a language model, you can put all the sequences into one sequence and have a end of sentence symbol or something in the middle. And this will usually be enough to have the system learn where the state resets for the RNN or LSTM. So that is one way. The other way is you can have buckets, and that's what we often do. For example, we build a graph for length 10, and we build a graph for length 20, and a graph for length 30. We put in the sequences in the right bucket, and then we do the forward propagation and the backward propagation, and then later we multiply the gradients with either a 1 or a 0 for a 1 if the length is still active, and for a 0 if the length is not active anymore. And we probably should have a better example that explains this, because it comes up so often. I will, when I go back, I'll see how we can make this a little bit better. Your second question was about the LSTM for speech enhancement. So we don't have specific things yet for that. This is something that users like you maybe can develop and share in some way with other TensorFlow users. For feature extraction, I'm not sure we can do everything in TensorFlow, but most of the feature extraction is usually done, the FFT and so on is done until the is done in a different module. So this is something that hopefully users can develop. There's one guy here in the front. Okay. Yes, I mean, I don't think there's anything mysterious about it. I mean, you have a function that you optimize, right? It's function optimization. And yes, there are many parameters. how you find the best parameters, there is a there is a global maximum. We may not be able to find it, but we know that many of the local maxima are also good, and that's what we are trying to find. So when people say, okay, we have all these parameters, 1 billion parameters, how can we interpret each of the parameters? That is something that is difficult. I mean, that is just part of the statistical nature of the system. We also, it's hard to understand sometimes errors, right? It's a mix of many, many different things. And if you know, for example, about the adversarial networks where, people specifically design examples that flip the classification decision from a cat to a dog, they can just flip 1 pixel in the image to go from a cat to a dog. So those are cases that make us understand this better. And I believe personally that in the future, we will probably use a lot less parameters for the same problems, which will be also much faster to train. And then probably we can see a little bit more, what each parameter does, right? Okay. There's somebody here? Okay.
I have a question about parallelism, the data parallelism and model parallelism. And maybe the TensorFlow is the only and stable tool to implement model parallelism. And last week you reported significant improvements of speed with inception model. And do you have any result or experiments to share about model parallelism with the TensorFlow?
So there are many versions of parallelism that we use, right? Data parallelism we use actually a lot. I mean, it basically means that each machine is reading different data and sends this, runs the model. Each machine has a copy of the graph. It runs the forward and backward pass through the graph and sends the gradient to other machines where they are updated. Or it could be actually all on the same machine. So we use this definitely a lot. So the model parallelism, by having different parts of the model on different machines, we also use a lot. So for example, what is often a problem is if you have a large softmax at the end, the large matrix multiplication, it takes a very long time just to go through this one matrix. And we cut it in many different pieces, in like 32 or so, and put it on 32 different machines, and only send the data to that machine, and that updates. We calculate the softmax, gather all the statistics and normalize for the probability, and then only update the parameters on that machine that we were on. And things like that we use all the time. Then of course we have. So for threading, there are 2 different ways. One is we can execute different paths of the graph in different threads on a single machine. And also, that probably the computation, many of the basic computations are done in Eigen. And Eigen has their own threading model that, if you do one matrix multiplication, you can cut it into many different pieces, as many threads as you have, and do it in parallel for those 8 threads. So all this is working at the same time.
Okay, so is there any significant speed improvements with model parallelism versus data parallelism with multiple machines, I mean?
Yes, I mean, we use inside, we almost never train things on only a single machine, almost never. And so, for example, some of our translation models we train on 120 GPU cards, right? And for a reason, because it makes it much faster. It's unfortunately not completely simple to decide what the best structure is. What we would like is that TensorFlow itself decides where to put all the nodes and to make it the fastest, right? But currently, because it's so difficult, we haven't, we don't have a fully automated system for that yet. But I'm sure at some point it will happen. for now, you have to, put your operations on certain devices most of the time and try to figure out how to make it really fast.
Okay, thank you.
You can finish. Yeah. So 큰 박수 부탁드릴게요. 네.
Okay, thank you very
very
much.
Yeah.
감사합니다.